In the old city of Königsberg, a river split the town into four pieces of land: a north bank, a south bank, an island, and an eastern quarter. They were joined by 7 bridges, and that raised a simple-sounding question. Could you take a walk that crosses every bridge exactly once? The townsfolk tried for years, on Sunday strolls, on foot, over and over. Nobody ever managed a route that used all 7 bridges once. But here is the frustrating part. Failing 1,000 times does not prove a thing is impossible. Maybe the 1,001st try would have worked. The breakthrough was to realize the geography does not matter at all. Not the river, not the shapes of the banks, not the distances or the pretty curves. None of it changes the walk. The only thing that decides it is which land connects to which, and by how many bridges. So keep just that, and bin the rest. So shrink each patch of land down to a single dot, and shrink each bridge to a line between dots. Throw everything else away. The whole city collapses into 4 dots joined by 7 lines. And now the puzzle transforms. Crossing every bridge exactly once is precisely the same as drawing this figure in one stroke, without lifting the pen or retracing a line. We have met that problem before. Now use the rule from the one-stroke lesson. Count the lines meeting at each dot. The island has 5 bridges. Each of the 3 banks has 3. So that is 5, 3, 3, 3. Every one of those is an odd number. 5 is odd and 3 is odd. So all 4 corners of this graph are odd, and every dot turns coral. There is not a single even corner anywhere. And that settles it. A one-stroke figure is allowed 0 or 2 odd corners, no more. This one has 4. 4 is more than 2, so the walk is impossible. Not unlucky, not too hard, impossible. A mathematician named Euler proved exactly this in 1736. And notice what changed. The townsfolk could only ever say they had failed so far. Euler could say it can never be done, for certain, forever. In settling a little puzzle about bridges, he invented a whole branch of mathematics, the study of dots and connections we now call graph theory. The real lesson is bigger than bridges. A problem drowning in detail often hides a simple structure underneath. Throw away everything that does not affect the answer and keep only how things connect. What is left is a graph of dots and lines, and often a clean rule answers it outright. Abstraction turned a hopeless afternoon of walking into one quick count of odd corners. Your turn. Suppose one bridge, the one from the island to the east bank, is washed away. 6 bridges are left. Recount the odd corners and decide. Pause and try. Losing that one bridge drops the island from 5 to 4, and the east bank from 3 to 2. Both are even now. Only the north and south banks stay odd, which is exactly 2 odd corners. So the walk that was impossible with 7 bridges becomes possible with 6, starting at one odd bank and ending at the other. One more the other way. Leave all 7 bridges, but build an 8th, joining the north bank straight to the south bank. Now recount, pause and decide. The new bridge lifts both the north and south banks from 3 to 4, making them even. That leaves only the island and the east bank odd, exactly 2. So one extra bridge turns the impossible walk into a possible one. That one afternoon by a river grew into a field that now maps road networks, electrical circuits, social links, the whole internet. All of them are just dots and connections, the same graphs Euler drew. The trick that cracked the bridges is the same one that runs modern life. Keep the connections and drop the rest. So a problem tangled in detail is often a simple one in disguise. Strip the map to dots and lines, count the odd corners, and a puzzle that beat a whole town for years falls in a single line. That's all for this video.